Okay, so here we have Stephen on the Ferris wheel, and his elevation given in meters above the ground at some time t in seconds is modeled by this equation here. Jesse thinks that Stephen will be close to the ground at t equals 55 seconds, but Jacob doesn't agree. What we want to do is calculate the average rates of change at times sufficiently close to time equals 55 seconds, using the difference quotient to determine who is correct. Okay? So we're going to start with the average rate of change, which is how we always do this. And so we've got h of 55 plus h minus h of 55 all over h. And that then becomes 5 cos 4, and then instead of time, we're going to put 55 plus h minus 10 degrees plus 6 minus 5 times cos 4 times 55 minus 10 plus 6 all over h. Just simplify things a little bit. So we get 5 cos 4 times 45 plus h degrees. We would have canceled out the 6's here, and that's minus 5 cos 180 all over h. So then, importantly here, what we're going to do is we're going to let h equal negative 0.001. And I know that maybe that's a little bit smaller than we really need here, but because we're multiplying by 4, after we added 45, maybe things will work out okay. So then the average rate of change lots of brackets here. So we've got 5 cos 4 times 45 plus negative 0.001. Again, all over. And now instead of h, it's negative 0.001. We simplify all of this. We end up getting 5 cos of 179.996 degrees minus 5 cos of 180, and so that gives us negative 4.99999 minus negative 5, and that then gives us negative 0.000115. I believe that's meters per second. Then we'll do the same thing with h being positive, so let h be 0.001. The average rate of change is going to be the same thing as we've seen in above here in this other example. So 5 cos of 4 times 45 plus positive 0.001 minus 5 cos 180 all over positive 0.001. And so we do some simplification, a couple other steps in here, and we get negative 4.99999 9. And so it gives us basically the same thing because we're on the same, about the same distance away from the maximum on either side. And this time we're divided by a positive, so that gives us now 0.0000115 meters per second. And then to finally finish this off, the estimated instantaneous rate of change is where we take the average of those two values. So we take negative 0.0000115. We add that to 0.0000115 and divide by 2. So we're not taking the average rate of change again with those, we're just taking the average of the two average rates of change closest to that value of t equals 55. And we end up getting this, and when we divide that out, we get 0 meters per second. So because we have 0 meters per second, and what we saw earlier in the lesson, that when you have 0 meters per second, that's a zero rate of change, which means that there's a horizontal tangent and that means that it's either a maximum or a minimum. Now the only way to figure this out, if it is a max or a min, meaning that either Stephen is the furthest away he could be or the closest to the ground, the only way to figure this out is if it's a maximum, then there should be a positive rate of change to the left of the max, a negative rate of change to the right of the max, or if it's a minimum, it would be a negative rate of change to the left and a positive rate of change to the right, in order to determine for sure if it's a maximum or a minimum at that horizontal tangent. Okay, so what you can do is, we know that 55 then is the max or the min, then maybe what you can do is find the average rate of change to the left of this, maybe get an average rate of change to the preceding that at t equals 53 seconds, and then following at t equals 57 seconds, for example, and then work out a couple average rates of change, one to the left, one to the right, and then you can determine whether it's a max or a min by the rates of change on either side of that horizontal tangent.